I was working at Empa, and I will share some of the results of the research I carried out at the Urban Energy Systems Lab of Empa. So let me start from the very high level. So I was working on a model that was meant to provide the optimal design and operation of energy systems involving different energy carriers and energy conversion and storage systems. We already had such a software or such a modeling framework at Empa. It was called, I guess it's still called eHabli, but the model was kind of tend to oversimplify the dynamic behavior of some components, and particularly those components that we were interested in, that are seasonal thermal storage systems, where the conversion and the storage efficiency depends on the system state. To overcome this problem, we formulated this, we developed this new model that we call BHAB, that uses bilinear constraints to describe such components, thus making the problem non-convex. We use Gurobi as the underlying solver. So one of the differences, I'm just making a couple of slides on the model, and then I will directly switch to the case study and to the results that I guess are more interesting. So one of the differences that we formulated the energy hub problem as using graphs, so that each component of the energy system could be defined as a node or an edge of a graph, so that we can identify a particular case study with a particular energy hub that can be described by an adjacency matrix, so that we individuate this energy system in a unique way. And once we have defined the energy hub, so how these components are interconnected, we can also change the models for each component. So if node 13 is an iStorage, we can replace the iStorage model by simply connecting the new model to the node 13. This is the idea behind BHAB. So let's go to the case study part, which I believe is more interesting. The first case study was the Empa campus, where we want to investigate, starting from a previous research by my colleague Massimo Fiorentini, the optimal design and operation of borehole thermal energy storage system. So when I say case study, I mean particularly the heating and cooling load profiles that characterize this set of 35 buildings with an energy demand for space heating and cooling approximately equal to 6 and 1 gigawatt hour per year, and the peak loads of 3 and 1 megawatt respectively for space heating and cooling. This is the energy hub that we want to optimize. That means we want to find the optimal size and also how to optimally manage all the components that allow the exploitation of a borehole thermal energy storage system. These components are the BTES itself, solar thermal collectors that recharge the BTES during summer, the conversion machines that allow to provide renewable space heating during the winter, so the air source heat pump, and a water heat pump extracting heat from the storage, and then an air chiller and a BTES chiller that rejects heat into the storage during summer. So during summer, we can provide heat to the storage either with the solar thermal collectors or with the BTES chiller. And this is how the results look like. As you can see, So first of all, we distinguish between a low temperature network supply, which is the case here with the 40 Celsius degrees supply temperature, and a 65 Celsius degrees supply that we will look at later. The optimal operation in this case means that we provide the base load during winter, as you can see here, with a water-to-water heat pump. So we extract the heat from the BTS, okay? And we provide the remaining heat, also covering the winter peak load with the air source heat pump. The corresponding average temperature in the storage goes from approximately 28 degrees here to over 40 degrees at the end of the winter in the spring. And the red part that you see here is what we call the bypass. So when the storage is hot enough, we can use the heat stored there to provide the heat directly without using the water-to-water heat pump, which cannot be possible when we have a high temperature network. So here we use the water-to-water heat pump also during the first part of the winter, okay? And during summer, as you can see, in both cases, we use the water-to-water chiller, and in part, the blue part here is the air chiller, and the rest is of the heat is coming from the solar thermal collectors. The same holds true for the low temperature case, although in this case, you can see the air chiller provides more heating during summer. This looks like an operating conditions, but it is much affected by what happens on the design phase, because the bigger the volume of the BTS, the higher the amount of heat that we can provide during winter. And this depends not only on the heating and cooling load profiles, but also on the CO2 price that we associate with this case study. As you can see, the higher the CO2 price, the higher the BTS volume, which is reasonable, because the higher the cost for CO2 emissions, the higher the investment in a seasonal storage. And the same holds true for the solar thermal collectors. So as you can see, we have an increasing trend. And this is like a kind of a Pareto front between operating costs and CO2 emissions. The second case study is an ice storage for the nest building that you probably know. So these are the heating and cooling demand that you see here for year 2021, okay? And this is the CO2 price. Yeah, so this is the collected from a weather station. These are the boundary conditions. The objective here is to store cold energy during winter for use during summer. So in this case, the energy hub looks similar, but it is slightly different because we only have, we don't have the water chiller here. We have a bypass pipe that can be used to provide free cooling during summer by using the ice storage, okay, provided that the ice storage is cold enough. And during winter, we can use either the water-to-water heat pump or the air source heat pump, as we did in the previous case. But here we don't use the solar thermal collectors because we don't want to store the heat during summer for winter, but the other way around. So this is the main component, and this is the bypass pipe. This is the ice storage model. It is slightly more complicated than sensible storage systems, because we also have the latent phase, where the temperature of the storage is constant and equal to the fusion or melting temperature of water. And what changes with the heat extraction and rejection from the storage is this variable epsilon. That means the water level in the storage. When we are in the sensible phase, the water level is constant and equal to 1, which means 100%. And when we extract and reject heat from the storage, we change the water temperature in the storage itself. And then we have all the other constraints regarding the heat extraction and delivery rate of the storage. Actually, there is an ice storage connected to the low temperature grid of Nest, which is a 69 cubic meter ice storage. Here you can see the construction works and a picture of the coils inside the storage, where we have a circulation of glycolized water, because, of course, we need to go below 0 Celsius degrees. This is what this is a comparison between the measurements of the ice storage during 3 years of operation on the Nest building. So, as you can see, we are able, so if you look this in the first graph, you can see that in blue and red, the heat extracted and supplied to the storage. And here you have a comparison between the model and the measured data. Of course, this is not a real validation, because the model we use in the optimization problem is slightly more simplified than this one, because here we need to consider also the change in the density of the water ice mixture depending on temperature. So depending on the temperature, we calculate the density, and the density gives us the volume of the water ice mixture. And since there is a water level monitoring system in the ice storage, we are able to compare the ice level calculated with the model, that is the continuous black line here, with the estimated ice level measured by means of this water level sensor in the storage. So we are able to capture the dynamics, okay, but as you can see, particularly in steady state operation, we have some differences that probably that are related probably to the sensor itself. Another very important component, not only in this case study, but in every optimization for the design and optimal operation of energy systems of this kind, is the heat pump, because depending on the performance of the heat pump, we have completely different results. So we used real operational data of the glycol to water heat pump of Nest. We made a regression and we used those coefficients to in the optimization problem that I will show you now. These are the results for two dimensions of the ice storage. The first is 140 cubic meters, which is approximately twice the, so double the real storage in Nest. And the second one is 420 cubic meters. Why didn't we use the 70? we use it, but I think it is more reasonable to show you the numbers and the profiles for systems that are able to cover a significant amount of the cooling demand during summer. So here you can see how the ice storage works in an optimal way. So it looks like the ice storage is used exactly in the opposite way of the BTS system. Because the BTS system, the water-to-water heat pump of the BTS system, if you remember, was covering the base load of the space heating demand of the Empa campus. Here, as you can see, the free cooling, which is the red part here, is covering the peak loads. And the remaining part, so the base load, is covered by the air chiller. So the free cooling, so the ice storage is used both to cover the cooling demand, but also to shave peaks during the cooling season. And if you look at the winter season, you can see a difference between the size of the storage. In the first case, so 140 cubic meter, we start extracting heat from the storage during late December. Instead, in the case of the bigger storage, we extract heat during the whole month of December because we have a larger capacity. Another interesting result is that the thermal insulation of the ice storage walls changes the optimal operation of the system. In fact, you can see that when you have an insulated storage that corresponds to the dashed line with 0.5 watt per square meter Kelvin, we don't use the sensible part of the storage as much as in the case with 2 watt per square meter Kelvin. Here, we take advantage of the heat gains that come from the surrounding ground because there is no thermal insulation, which means that in October, we have 15 Celsius degrees, and we can use this part of the sensible part to provide space heating to nest with a water-to-water heat pump connected to the ice storage. Instead, when the ice storage is more thermally insulated, we don't exploit that much the sensible part, but we can provide more space cooling. As you can see here, we can cover a higher amount of the cooling demand during summer. If we look at the overall performance of ice storage systems over the year, we can do it using 2 indicators. The free cooling ratio, that is the ratio between the free cooling supplied to the building and the overall cooling demand of the building, and the seasonal storage of the cooling of the ice storage itself. As you can see in the insulated case, the free cooling ratio is able, so the real, if you look at the real system, the numbers would be these ones. So in the optimal case, with the real ice storage systems that is installed in nest, we can cover 6% of the cooling demand, and the system has almost 30% of seasonal efficiency. If you look at the thermal insulation, the case with the assuming thermal insulation, of course, the numbers increase. But what I want to show you is that although the seasonal efficiency is almost double if you move from uninsulated to insulated storage. For example, if you compare 37% seasonal efficiency to 71%, it means that if you insulate the storage, you increase the seasonal efficiency by twice. But if you look at the free cooling ratio, the increase is not as such, because you have an increase from 18% to 25%. So what I want to say is that seasonal efficiency gives us only partial indication on the effectiveness of ice storage systems, because in the end, what we care about is how much of the cooling demand we are able to cover. And as you can see, we can also exploit the sensible part of the storage during winter. So seasonal efficiency, I don't think is such an interesting indicator as the free cooling ratio for this kind of systems. Let's come to the economic part. This is tricky because we want to compensate the investment for the ice storage by having lower cost for cooling. So you should compare the column of the LCOE, and if you look at the results with the seasonal storage, the only result which is similar in terms of LCOE to the situation without ice storage is the one with the highest volume due to the economies of scale. But this is very dependent on the cost correlation that we use for the ice storage. Another result, which is not that beautiful, let's say, because we spend a lot of money to have a nice storage, and we save overall 17% of CO2 emissions. Why? Because we are moving loads from the cooling season to the heating season. So we are shifting energy from a period with a low CO2 footprint of electricity to a period with a high CO2 footprint of electricity. So, of course, we have some benefits with the ice storage, but we should be aware of these problems. So, when should be the best situation to install an ice storage for seasonal load shifting? We compare the situation in 3 different climates in the US. So as you can see here, we took the reference small office building from the Department of Energy as a case study. So it is a virtual case study now. But just because we want to make a kind of a sensitivity analysis on the effect of the weather on such performance. And here you can see the share of heating and cooling demand. It is almost the same in Buffalo. It is skewed on the cooling demand in Denver, and the other way around in International Falls. And also you have some indicators here, like the minimum temperature. They are very cold places. We choose these places because we believe that the first important condition is having a very bad alternative to the ice storage. Okay, very bad alternatives means that using the air as a source is very bad. So of course, when the air temperature falls below 0 degrees, it is better to use the ice storage as a heat source. So compared to the previous case, we only added a new component, which is the PV system, to our energy hub, but the remaining system is the same. This is how the profiles look like. This is just one case where you can see that the same trend, you have the same trend. So the ice level increases during winter and then decreases during summer. Here you have the increase starting in January and not in December. And also we have the effect of PV system, which means that the cooling that we save during summer could be actually for free because we have local renewable production. So the effect of the ice storage, the benefit of the ice storage can be compensated by a higher PV system. And in fact, this is what happens if you compare the results for the 3 locations. On the left, in the first 2 graphs, you have cooling and heating demand covered by the ice storage. As you can see in the left part, the coldest location, which is International Falls, is the one with the highest share of the cooling demand cover compared to Buffalo and Denver. If you compare the heating demand, of course, we have the opposite situation. So the, let's say the warmest location is the one that provides the highest share of heating demand covered by the water-to-water heat pump or glycol-to-water heat pump connected to the ice storage. But the most interesting part is here, in my opinion, and this tells us that there is a trade-off between the ice storage size and the PV system size, because the higher the volume of the storage, the lower the size of the PV system. Because as I told you before, part of the cooling that you save through the ice storage could be provided for free. So it doesn't make sense to increase the size of the PV system too much when you have an ice storage, and vice versa. If you have a PV system, you probably don't need to increase the storage volume too much. Finally, when it comes to the economic part, and you compare the 3 locations, you should not be, let's say, you should not compare the absolute values of the 3 locations, but in my opinion, the most interesting comparison is between the first and the last point for each location. Because the first point means having no storage at all, and the highest point, or let's say the point on the right, means that you have a big ice storage. So as you can see, in Denver, which is this line here, and in Buffalo, there is quite a significant difference and gap between the situation with and without ice storage. But if you move to a colder climate like International Falls, for the reason I mentioned before, the difference is lower. So by this interpretation of the results, it means that colder locations are more suitable to ice storage systems. These are the references of the results I was talking about, so you can have a deeper look. And for both the BHub documentation and its application to other technologies like phase change materials or thermochemical storage, feel free to ask Massimo Fiorentini, because he's still working on these topics under the SOTES project. So I want to thank SNF for providing the funding for this research that was funded, that funded the Synergia project called SOTES, which is also looking at the social acceptance of these technologies in collaboration with the University of Bern and Hochschule Luzern. And finally, let me spend the last 30 seconds to let's say, spend a few words on what I'm doing now. So I'm more focused on the energy consumption of buildings at urban and also at national scale. So this is now my research, and I would be happy to share such results in the future if you're interested also in what we are doing here. So I finished my presentation, so if you have any questions, I would be happy to answer.